Now that we know our Thevenin equivalent resistance and our Thevenin equivalent voltage, we can redraw our circuit with our inductor placed back in the circuit with a single resistor of 200 ohms and a single voltage supply, 40 volts. And our inductor has a value of 5 Henry. So from that we can determine the time constant for our energizing of the inductor. So it's 5 Henry over 200 ohms, which is 0.025 seconds or 25 milliseconds. We know that as soon as the switch is closed, the inductor behaves as an open circuit because it wants to resist the flow of current. So the voltage across the inductor as a function of time starts off as a maximum voltage of whatever the battery is, 40 volts, and then it exponentially decays according to the time constant. And if we know what the voltage across the inductor is, we can also write down what the voltage across the resistor is, because Kirchhoff's voltage law still has to be satisfied. So the voltage across the resistor needs to be the voltage of the source minus the voltage across the inductor. So this is 40 volts minus 40 volts e to the minus t over the time constant, which we traditionally write as 40 volts 1 minus e to the minus t over 25. So this means that the voltage across the resistor builds up over time while the voltage across the inductor decays over time until eventually it reaches steady state. And then the current through the inductor we can write down as the voltage across the resistor divided by the resistance. So this is 40 volts over 200 ohms. 1 minus e to the minus t over the time constant. So the current is going to be 0.2 amps, 1 minus e to the minus t over 25 milliseconds. So we have determined what the question has asked, which is what is the current across the inductor as a function of time when it is in a state of energizing when the switch is closed. Now it's left in a steady, it's left in the closed position until it reaches steady state, and so when it reaches state, the current through the inductor is just 0.2 amps, which is essentially the maximum value that it can be. Remember that when it reaches steady state, the inductor behaves as a short, so it's as if I have only one voltage supply and one resistor in the circuit at steady state. And so the current would have to be 40 over 200 ohms. Once the system reaches steady state, the switch is opened back up again, so we could go back to our original picture and we can look at what that picture would look like if I opened up that switch. And if I open the switch, the voltage supply, the 240 ohm resistor and the voltage supply would no longer be part of the circuit, but the two resistors in parallel would be part of the circuit. So I can redraw that picture again when the switch is opened back up, and it would look something like this, where I have my inductor, I have R4, and I have my total equivalent resistance for those two resistors in parallel, which was 160 ohms, and then this is R1, which isn't going to contribute anything because it is not connected to the inductor in series. So as soon as the switch is opened back up, the polarity across the inductor actually switches. So this is the original polarity across the inductor, but the current was flowing through here, through the inductor to the right, and so the inductor wants the current to continue to flow, and so the initial current in this circuit will be what the current was when the system had reached steady state, which is 2 amps. And we can determine the new time constant. So still the inductor is 5 Henry, and then now the total resistance for this loop is 160 plus 104 ohms. So that's equivalent to 264 ohms. So this gives us a new time constant of 0.0189 seconds, which is equivalent to 18.9 milliseconds. So now that we have our time constant, we know that the inductor is basically behaving as a current source to start with. And so initially the current through the inductor is whatever the current was right before the switch was opened back up and the inductor begins to de-energize. So it's 2 amps continuing in the same direction, and the current exponentially decreases depending on what that time constant is. Once we know what the current is, we can determine the voltage across each one of those resistors. So across resistor 4, it would be the current times the resistance. So this would be 2 amps e to the minus t over 18.9 milliseconds times 104 ohms. So the voltage across resistor 4 would be 32 volts e to the minus t over the time constant. Oops. And we can do the same thing for the total equivalent resistance of those two resistors in parallel. And so this would be 2 amps e to the minus t over the time constant times that resistance of 160 ohms. So that particular voltage is 20.8 volts e to the minus t over 18.9 milliseconds.